I now have the honor to introduce Roger Blandford, Crafoord Laureate in Astronomy this year, in addition to Professor Kerr. He grew up in Birmingham, got his education, including his PhD, in Cambridge, and served there as a research fellow for some years. Together with his student Roman Snarniak, he devised a famous mechanism for the extraction of energy from rotating black holes. He then moved to Caltech as assistant and then full professor, and in 2003 he became director of the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, and served in that function until a few years ago. Now he is professor of physics at the Stanford Linear Accelerator Center. He has worked on cosmic rays, white dwarfs, neutron stars, and black holes, gravitational lensing, and cosmology. He has also served in important governmental committees setting priorities in research. The title of Roger Blandford's talk is Engaging the Black Hole. So please. Okay, thank you. Almost, yes. Okay, I just want to get this out. Same, okay. Okay, not quite. Okay, all right. Okay. It's a bit expectation. Well, thank you very much indeed. It's truly a great honor to be here, and I'm delighted and humbled to receive this wonderful award, especially with Roy Kerr, who I've greatly admired and whose contribution is a singular one, if I might say, which has made all of this possible and opened up a whole realm of science for the rest of us. Thanks to the Royal Swedish Academy, thanks to the Crafoord family and foundation, I had the pleasure to meet in Lund. And the talks we gave there were popular talks. I think I might describe this one as an unpopular talk. And I'm going to cover, in some sense, much the same material, but at a sort of faster pace and with more sort of expectations of the audience in terms of what is known about the background in astronomy. And for some of you that will be a bridge too far, and for that I apologize, but I hope that everybody can get something out of this. It will also perhaps be unpopular in the sense that some of what I have to say may be a bit controversial or a bit different, and so that I'm not apologetic about, because I think this is a wonderful opportunity to have some discussions at this symposium, and I can be straightened out by my friends and colleagues, to whom I thank for showing up here.
to set me straight about some of these matters. The title, Engaging the Black Hole, is a bit of a nod to John Wheeler, who wrote, he didn't actually, I think, first coin the phrase black hole, but he certainly popularized it, and more importantly, understood and proselytized, particularly in the physics community, a much more modern way of thinking about black holes. And it's great that Kip Thorne and Remo Ruffini, who both, of course, worked with John and read books with him, are here. And so it's a bit of a nod to a famous article he wrote, I think in 1965, called Introducing the Black Hole, which I think influenced a lot of people to take these structures more seriously. And of course, it was at that time, as Roy has just said, that quasars had been discovered and people were starting to realize the implications of this observational astronomy. And so everything sort of came together in the 60s, before my time as an active researcher, but one that I was a great benefit for all the wonderful work that was done very fast in that decade. So, so this is a very compressed history here, and each of these, you know, could be, this is a sort of a lecture course in some sense here, but for many people who have seen this, and I'm just going to make some sort of propositions, if you like, about black holes in astrophysics. And so this is the astronomer's view, if you like, of black holes, as opposed to the theoretical physicist's view, or the mathematician's view. And they're all valid and they're all distinct, but I'm just going to put on, wear my astronomer's hat here, and say about some of the things that they will take seriously, that other people will have a different set of assumptions, if you like. So astronomers will by and large believe that GR is correct. The principle of equivalence, of course, the weak field test, the indirect and now direct measurement of gravitational waves, that's good enough for an astronomer. Now, there may be critics around there and so on, but that's great. The black holes for an astronomer are just really mass and spin, and that's because the charge, although terribly important in theoretical physics, Kerr-Schell-metric and all of that, is going to be discharged very quickly under most astrophysical conditions, and is not gravitationally supporting. So the electromagnetism that I will discuss is one that's done in a passive Kerr background. The mass is just basically a scale. We're dealing here with just classical physics of length, time, and energy. There is accretion, as was mentioned, and there's power. There's a famous gravitational power here, which is what comes up in the theory of gravitational radiation, and we'll certainly hear more about that. They're associated with the accretion. There's a famous accretion rate, the Eddington rate. It was actually introduced for massive stars, and it's a power, and it's the radiant luminosity. It's a very important scaling power, and it's when the radiation pressure opposes the pull of gravity. And associated with that is an accretion rate, or equivalent timescale, first taken seriously by Salpeter, of a cosmologically interesting time of about 500 million years. So the spin of the black hole is very important. We know observationally in astronomy, and that is taken just from the Kerr metric. And again, astronomers will take the simple view. They won't be worried about firewalls. They won't be worried about gravastars and other constructs. Well, I'm very excited about hearing from David Wilshire and Herr Tooft about some of the theoretical physics aspects of this, but for the astronomers, as you heard from Roy Kerr, they are terribly conservative and slow on the uptake when presented with new exciting theoretical developments. So I'll be one of those today. An important feature, of course, of the Kerr metric is that there's an innermost stable circular orbit, known economically as the ISCO, and then what an observer will see from these will be characterized by a Dopplership redshift deflection and so on. Astronomers will know about the dragging of inertial frames, and they'll have seen various pictures about this. And just to sort of throw in a sort of a little aside here, and I get taken to task by this, is that the dragging of inertial forms is very much a coordinate-dependent phenomenon. And if one imagines just a gyroscope going around in orbit around, just say a Newtonian gyroscope going around a sort of Newtonian orbit, and one measures the angle of the direction of the gyroscope, say in the equatorial plane, to the radius vector from the object, and as you go around, the gyroscope of course points in the same direction, but the radius vector goes like that, and so that angle will proceed in a circle. Now, if you do that in a Kerr metric, you find that this is just the equation. Exactly the same thing happens, and there's no sign of the rotation of the black hole there. There's no mention of A or the angular frequency of the black hole, and so it's exactly the same thing. So this just shows you it's a coordinate-dependent effect. It's terribly important, of course, but this dragging of inertial frames has astrophysical consequences. Another thing that has astrophysical consequences is what one may call the irreducible mass. If one uses the area of a black hole to define an irreducible mass, which we'll call, I like to present it whimsically in this form, in the way that's similar to special relativity, we can write the actual mass of the black hole to the irreducible mass, the minimum mass that it can be reduced to in this form, which is familiar from special relativity, where this is the characteristic speed, which I've just written in that form, and omega h is the angular frequency of the black hole. So this is just a little bit of whimsy, if you like, but more importantly is the fact that there's 29% of the mass is there for the taking in rotational energy, much the same way as it's there from the taking from a spinning neutron star. And this region from which this sort of spin energy in some sense exists and is extractable is called the ergosphere, and Ramo is one of the people who understood the importance of this. Sorry? Yes, I said Ramo was one of the people who did this, yes. Okay, so black hole astrophysics in 2016. So what do we have? Well, we know that stellar and massive black holes exist. In addition, there's the possibility, but not the complete proof, I would say, of intermediate mass black holes, which is between stellar mass scales and massive scales. There's primordial black holes, which people have sought seriously and not yet found, but there's currently, and we may hear some about this later, a lot of excitement about the possibility that some dark matter could be in this form, and I'm interested to hear opinions on that. There are mass measurements now, including from the last Crafoord Laureates, and so we know in the stellar scale it's from 4 solar masses from X-ray astronomy up to now from gravitational radiation. We've seen the birth of a 60 solar mass black hole, and then if we look in the active galactic nuclei, somewhat less than 1 million solar masses to more than 10 billion solar masses. That's the range of masses that are being measured by a variety of astronomical techniques. The spin measurements, and we'll hear about this from Andy Fabian, are pretty convincing. Most of the measurements, and there could be a selection effect here, are high spin, and claimed values of the spin parameter that Roy just mentioned are up to about 0.99. Again, we'll hear more critically from Andy about that. There's magnetic field present. Not only is this theoretically seems unavoidable, there are dynamical instabilities in conducting accretion disks that produce magnetic field prodigiously, so you can't do away with it, but we also have Zeeman and Faraday measurements of accretion flows that have to be magnetized. We see the observational evidence of those magnetic fields. And quite recently, there's been the best evidence yet from a stellar black hole of the presence of copious amounts of positrons made presumably by pair production in the vicinity of the black hole. And then finally, very importantly, observationally, is the range of accretion rates that one encounters are from the very low values, for example, in the black hole at the center of our galaxy, all the way up to the gamma ray bursts and the tidal disruption events where one gets stellar massive gas processed very, very fast, an enormous accretion rate. So there's a very large dynamic range of accretion rates that we observe in astronomy. Okay, moving on quickly. Now I'm going to make, these are huge topics, each of these, and I'm just going to sort of almost list them here. And you'll hear more about this from subsequent talks, but these, if you like, the components of the engineering system that we're looking at. There are accretion disks, and these can be thin, And most work has been done describing disks when they can cool very efficiently. They're geometrically very thin, and they radiate like flat stars. That's the way that's been thought of, but there has also been a lot of attention in the last 2 decades or so paid to thick accretion disks, which do not cool well, and so are more like a torus when they surround the black hole, when they orbit the black hole. And then don't forget the fact that the supply of gas may not know about the direction of the spin of the black hole at large radius, and so these disks can be warped, which has enormous observational implications. The winds are likely to be made. We know these winds are present observationally, and they are expected. It is very easy, as in the case of the sun, to lose a lot of mass from an accretion disk. One way in which this happens that is very important, and I'll say more about this, is that the torques that are created by the magnetic friction inside the accretion disk transport angular momentum outwards. They also transport energy outwards. And so that transport of energy has to be gotten rid of, and in a thin accretion disk, that energy will just be radiated and be there for the gratification of observational astronomers. But when they're adiabatic, when that gas cannot radiate, then it will thicken the disk, and in fact it is so much energy that is transported outwards inevitably mechanically by a torque, not in any model-specific way, and that will unbind the gas. It'll be carried off in the wind. That seems almost unavoidable. The way in which this is most likely to happen, in my view at least, is that it is a magneto-centrifugal wind, just like in the sun. Magnetic fields are important for launching the wind, but also radiation pressure, we know observationally, is important in driving these flows away. And it is going to be very hard to understand the details of all of this physics, just like it is in the sun, but I think it's unavoidable that it happens. Jets are another component of this system, and here's one from Andrew Wilson, a long time ago, Pictoray, and I think it's the most beautiful example. This is the nucleus of a galaxy here, and this straight X-ray structure here, ending in, if you like, a beam dump up there, is it's just a line on the sky, dead straight. And this is an outflow that sort of combines all the instabilities known to theoretical physics, and it ought to be wandering around all over the place, and yet this is what the X-ray astronomer sees. That's a truly remarkable phenomenon. This is perhaps the most extreme example of this, and that's, well, of course, one of the things we're trying to explain. And obviously, I'm going to argue that the power from jets like this comes from spinning black holes, but it is also necessary to understand the external boundary conditions that provide the collimation for this. Stars are also accreted onto black holes through tidal capture, and also stellar mass in a gamma ray burst, in a collapsing star, for example, or in a neutron star binary. And again, we see observational examples. Less gamma ray bursts once a day, and so we see now many examples of tidal disruption events and tidal capture of stars. Again, those are ways that black holes can grow. And then finally, and most dramatically, and this is the biggest excitement in this business since the Kerr metric, surely is the measurement of gravitational radiation from this one event so far, but surely many more to come. GW 150914 here, and here I'm not going to say very much about this. It has been, a wonderful reward, if you like, for scientific audacity, and combined with skill and patience over a 30-year period. And this says everything more eloquently than I can. But you'll hear talks here from Kip Thorne, Laura Catanati, and Hans Pretorius, who will tell you much more about this, and indeed what is to come from both an observational and experimental and a theoretical perspective. Moving on. So here's some sort of ancient principles. I've already said this. If we've got just a simple stationary disk, I'm going to say there's a torque, and just generically here, although we have some understanding of how it comes about from magnetic stresses and so on, it will be equated to, in the simplest case, and this all generalizes relativistically, into the mass accretion rate, m dot, and the specific angular momentum. And associated with this is an energy transport, because the torque does work at that rate. And this causes a local heating when you add it all up, which is 3 times the local release of gravitational energy. And you might think you're getting something for nothing, but the sums all work out because the extra energy comes from the inner edge of the accretion disk. And so it all actually works out in the end. And so we get energy released, and if it's radiated away, we believe this happens when the mass accretion rate is comparable with the Eddington rate, and we can argue about what the precise numbers are there. And so this should be efficiently radiated when it's an intermediate mass supply rate. If you want to supply gas at an intermediate rate, that energy should be radiated away, and this should be the power that you get locally. Another feature of these stationary thin disks is this innermost stable circular orbit. The ISCO will shrink from about 6 times the gravitational mass as expressed as a radius for the black hole, down to 1 times that, almost, but not quite, at the horizon, as the spin parameter goes to its maximal value. By contrast, in adiabatic accretion, we believe, and there's good observational evidence for this, I think, and we're going to hear more from the simulators, that the mass accretion rate is much less than the Eddington limit. The plasma cannot cool. You get this thick torus that's supported by ion pressure. Conversely, when the mass supply rate is much greater than the Eddington limit, you have the problem that the photons cannot escape. They are trapped in the infalling gas. And so again, it is adiabatic, and you get a radiation pressure supported torus. And in this particular second case especially, you're likely to get, as I said, a lot of the energy carried off in the wind. Moving on, again, this is all fairly standard, but I'm just here. So what happened? Did I go back? Oh, yeah. Oh, that's the. I meant to show that. That is the innermost stable circular orbit in an unspinning hole, and what it would look like schematically in a spinning hole. That's right. Okay. So, as I've already mentioned, the disks are magnetized, and we now have very good simulations. You may see a little bit that, I'm not sure in the subsequent talks, of the nonlinear magneto-rotational instability. It is highly effective. How it works out in principle, how it connects to winds, is still very much a work in progress. But we're confused on a much higher plane than we were a decade ago, thanks to wonderful numerical simulations. The torques are large. The extent to which this produces dynamos is, I think, again, also a matter of controversy. I was at a meeting all last week where this was a fairly big deal, and I stand by my statement that it's a matter of controversy. I mentioned this magnetocentrifugal wind. Here the idea is that if you've got a vertical field through the disk, it will be carried around by the orbiting gas, and if you make it be inclined to the vertical and going outwards, then the gas will be flung outwards. And then the inertia will create toroidal field, and that will be sort of wrapped around the spinning axis or the symmetry axis, and it will collimate an outflow, and so you'll get this wind that will be collimating, and that will be very important for collimating the jet that derives from the spinning black hole. The speed of this wind is likely to be a few times, we're not quite sure how much, the orbital speed at the foot point. As I said, radiation is also important. Now, if we now try and play the same sort of game with a spinning black hole, and this was work that I did with Roman Znayak in what I regard as one of the most felicitous, in two senses of the word, collaborations I've ever been involved in, and I'm thrilled that Roman was able to come to this meeting. The basic idea is those magnetic field lines that here are threading the disk can also thread the horizon of the black hole, supported by external current. So it's not autonomous to the black hole, it really needs this disk outside, and it will provide some collimation as shown schematically here. And the horizon will essentially rotate with an angular velocity like this, and it has a radius in the appropriate radial coordinate given by this expression here. And oversimplifying a sort of slightly more complicated condition, the horizon is a fair conductor, and overall, we actually know what its conductance is, but overall it's about 100 ohm resistor. And so these field lines here will not be carried around perfectly as they will by the disk with the angular frequency of the disk. They'll slip somewhat, and I like to think of this as a bit as a sort of magnetic clutch. And so that's why I call this engaging the black hole. This is a sort of motor, if you like, a sort of mechanical way of thinking about this. So these field lines act as a bit of a magnetic clutch between the black hole itself and what's going on outside. And if we, so they have a sort of compromise angular velocity depending on what's happening outside. And if we think about a resistance associated with a little bit of flux surface here, and I'm going to just give that schematically a resistance RH, and then I imagine a load up here. It could be the out part of the accretion disk, it could be an outflow, and we can define that too. Then this magnetic field lines here will move with a sort of compromise angular velocity like that. And so that's the way, and that can differ as we go from the pole to the equator in this outflow. So here's how this works out in terms of angular momentum and energy. If you make the simplest stationary axisymmetric force-free solution, so stationary, axisymmetric, not like the real world, where there are instabilities and so on, force-free, where we ignore all inertia, it's just the electromagnetic field, no inertia terms are significant there for the matter. And so if we just do that, then the simple solution will have electric fields of order the magnetic fields generically, and these flux surfaces shown here in a numerical simulation, from my colleagues Jonathan McKinney, who's here and going to speak later, and Sasha Tchaikovsky. And along these flux surfaces here, we have conserved quantities, the angular frequency of the field line, the current interior to that flux surface, a voltage, these are equipotentials, a voltage from the axis to that flux surface, an angular momentum, and a power that are carried interior to that flux surface, so the energy, electromagnetic energy and angular momentum flow along those magnetic field lines. These are, of course, is all defined in a relativistically correct way, but I'm showing it schematically here. And there will be conserved energy outflow in the non-rotating frame. That's from the same Killing equations that Roy just mentioned. But if we think about an observer hovering above the horizon, just moving with an angular frequency omega h, then that observer will see energy appropriately going into the horizon. From a thermodynamic viewpoint, using the first law of black hole thermodynamics with the temperature of surface gravity here and the mechanical term here, then what's going on is some increase in the mass of the black hole and obviously an increase in the irreducible mass. And this is, if you like, an electromagnetic expression of the process that Roger Penrose first thought about, whereby you could, by a thought experiment, extract the spin energy of the black hole. There are going to be two light surfaces in here, and within that light surface, in the context of this sort of solution, matter must go into the black hole within the innermost light surface and go outwards at the outer one. And so we have to create charges in there, but under the most astrophysical conditions, the minimum amount of charge that you have to create is tiny and has negligible inertia to carry all the relevant currents and charges under astrophysical conditions. What happens in practice, of course, is much more controversial. So I'm now going to say a little bit about the numerical simulations, and you're going to hear much more and authoritatively from Jonathan McKinney, but this is an exercise I've been carrying out with a graduate student, Richard Anantua, and I'm going to call this observing numerical simulations. And just not to offend the true astronomers here, I'm going to use a lowercase o for observing in a simulation, and an uppercase O for the real observation using a real telescope of one form or another. So, but I think observing simulations is very good, and many people here have been engaged in this, deconstructing what the simulations are telling us, not just producing some number. So, there is really no common understanding of AGN anatomy, especially for jets, and I would say the physiology is also in a somewhat confused state, in particular the identification of the emission mechanism, and we'll come on to that in a moment. There's the biochemistry is another part of the jets, and I think we really do not understand this. This is the dramatic particle acceleration that is required in these structures, and it's very easy to say, oh, it's just shocks or something like that, but in practice, that is not an explanation at all. There's a lot more work to be done. We know it has to be efficient, and we know it has to be very variable. Now, but what I am going to do is take these simulations seriously and take the observations seriously and associate the inner jet with the magnetic flux that threads the black hole. There may be a wind from the accretion disk, but I'm going to say the relativistic jets that you see are identified by the flux that actually threads the spinning black hole. I'm going to take that seriously. It might be wrong. A lot of it, obviously, as you go further out, its interaction with the environment becomes more and more important. And let's just see where that takes us. So here's M87. I'm going to just use 3 examples here. M87. And here's the capital O, so this is what's actually come out of telescopes. This is LOFAR, which Onslow, just up the coast, the coast of western Sweden, where it's been it's part of the low-frequency observations. Here's the X-ray image of the Virgo cluster. Here's the M87 galaxy. Here's a Chandra image of the jet that comes out of the 6 billion solar mass black hole in the center. And then VLBI observations, and I'm not going to show the most recent work because Avery Broderick, I'm sure, is going to show this. But let me just say that we are now tracing using very long baseline interferometry down to roughly times, at least seeing structure on the scale of about 10 times the mass of the black hole, and with hope of seeing much more than that in the future. So if we try and make some guesses as to what's going on in this jet, then if we say that it has got to keep the Virgo cluster hot and emitting X-rays, then it needs about 310 to the 37 watts. The jet itself appears to be roughly paraboloidal from the observation, directly from the observations, and that's at least interpretable by simulations. It looks like it's an inclined angle of about 20 degrees. The accretion disk is remarkably invisible, and I would claim that it's a very good example of a very low mass accretion rate at this time, and so it's an example of adiabatic accretion, and this is the measured black hole mass. So, and then polarization is seen here, which is again indicative of strong magnetic fields. Now, if we take the simulations sort of seriously, and here's the innermost part here, then if we say the jet is really luminosity is really as high as is required to keep the cluster hot, then this is going to be the mass accretion rate. And if we try and say that what confines the jet, confines this surface at the black hole, is the gas pressure of the accreting gas. This doesn't have to be the case, but this is what the simulations have generally assumed. Then that has an important electromagnetic consequence, is that if we might say a current goes up there like that, there's got to be a return current that comes back, and that return current has to be on the outer edge of the jet, on the outer edge of the jet. So there's a outward current like that, and then a return current comes here like that, if this is confined by gas here. That's unavoidable. So if you say that there is this force-free behavior, and if you look at the simulations are quite consistent with this, that there is force-free behavior out to at least about 100 M, and that means the voltages here are 100 exavolts. That's 10 to the 20 volts. That is enormous, and those familiar with particle physics, I hope they're impressed by that. The currents should also impress some exaamps. The angular frequencies are preserved along these field lines in the simulations out to about 100 M or so, and the flux, that should be a flux phi threading the hole, something got lost there, is, for those of you familiar and totally comfortable with SI units, which is probably no one in the audience, that is 100 Jota Weber. Okay. It'll come. Okay, beyond 100 M, what one can see is going on in these simulations, I'm observing the simulations here, is you are transitioning from force-free to a genuine MHD. You entrain mass from the outside, you accelerate, the current crosses the field lines, pushes a J cross B, pushes what gas there is there out, so it gets faster and faster, and so we get an accelerated jet, and the outer edges of the jet, there's a sort of boundary layer that spreads and spreads and spreads. And in the case of this source, eventually, I think it will be the wind and will slow down the jet. And this is what's called a Van der Rohe-Riley type 1 class source. And so it'll be decelerated by the actual wind. Okay, So if we go now to my second example, which is 3C279, this is a luminous quasar. In fact, it was historically 11th magnitude. It's an extremely bright distant object. Okay, I'm running out of time. I've got serious time problems here. Okay, so it is a luminous radio quasar, and it has got a very powerful disk luminosity, which we can see, unlike in M87. This is the typical power that's inferred in the jet, and we see it in gamma rays. This is the observed flux that's measured, and you see it's completely dominated by the gamma rays. And the gamma rays are, we believe, relativistically beamed from the jet, but still they're dominant. This is predominantly a gamma ray source. Now, it has been a thing that one teaches students, that when you get this two-humped profile here from the low radio frequencies up to the highest energy gamma rays, you get a sort of two-hump profile like that, and that's synchrotron radiation and that's Compton radiation. I'm not at all sure that that's the case. In the case of the gamma rays, we're right up here, and instead I'm going to argue that those are in fact coming from very close to the black hole, unlike in most models, and they are synchrotron radiation. The Lorentz factors of these outflows are measured by radio astronomers to be 30, so they're moving almost at the speed of light, and so it's heavily beamed, and so this flux is an exaggeration of the total power in the jet. But the variations now have been seen, and this is a recent result that will be coming out in a few weeks from Fermi, vary in 5 minutes. So that's really, I think, nails the case that the gamma rays, which is most of the power, come from very close to the black hole. And so, in fact, they come from as close as they can from what I call the gamma sphere, which is where you can avoid pair production on soft photons from the accretion disk. So this is the observations with a lowercase of the trying to apply these numerical simulations. Here the voltage is going to be up to a zetavolt. That's 10 to the 21 volts, which of course relates why these are good candidates for the ultra-high energy cosmic rays. It's a marginally radiative jet. These are some numbers here, if you like, associated with it. And this is the synchrotron photons go up as high as about 300 MeV in the co-moving frame, which is just about the synchrotron radiation reaction limit. So this is, I think is a much better interpretation than it being Compton scattering. And in fact, there's a generalization that can explain TeV gamma ray emission, and this will only be, I think, relevant for the experts here, where you can actually make even the TeV emission as synchrotron radiation. If you accelerate protons to enormous energy, have them pair produce on the radiation field, and then you make enormous shafts. And so you can, in fact, make the TeV gamma rays as synchrotron radiation. Next one is, the final case is the Seyfert galaxies, which Andy is going to tell you about. Here are the observations from 1995 of the ion line, and interpreting those observations in a way that he will explain to you what is thought to happen is that there is a source of continuum radiation down here, and that illuminates an accretion disk down here. The X-rays that are responsible for the ion line and much else besides come from this accretion disk. And so the question is, what is this so-called lamppost up here above the spinning black hole? What is the source of this continuum radiation? What I'm going to suggest here on the basis of these solutions is, if you imagine a thin accretion disk, schematically a little loop of magnetic field emerges just like it does in the sun. The differential rotation takes the foot point here faster around the black hole, or the blue hole as it appears to have worked out, relative to that foot point there, and this will expand, and so we'll have lots of these loops of field twisting around the black hole, and they will twist mostly along this axis here above the black hole. The field lines will reconnect dramatically all the time, and that reconnection will provide the heating, I assert, for the lamppost, which then sends X-ray photons down to illuminate the disk. I won't go on to this, although that's an amusing possibility. Now, the final thing I'd like to say in my -1 minute or whatever it is this is more a slogan than a mechanism, but it's what is the real largest missing piece of this story, I don't know if the story is correct, but I will certainly say that this part is missing, is to understand how the particles get accelerated. We know the radiation physics, we know quantum electrodynamics and so on, we trust all of that, but we do not understand particle acceleration. And what one needs in these and indeed other sources is ways of rapidly converting electromagnetically dominant energy into high-energy particles, efficiently and with essentially the maximum energy. Now, one way to do this is just to have oppositely directed magnetic field lines reconnecting that do that. So they just exchange partners like that, and that will have some dissipation associated with it. It goes on, it's efficient relativistically. I question if it's efficient enough to explain the observations. Another thing that can happen that I actually quite like is we think about these magnetic field lines in the way that Hannes Alfvén used to advertise them as having little, mathematically we call this helicity conserving, and so you do something like that. It doesn't change the helicity. That can happen dynamically at a much faster rate and can reduce electromagnetic energy and make charged particles very fast. So just to show you some ways in which this can happen, this is a process that I call magnetoluminescence, a little bit like sonoluminescence, and this sort of very rapid flaring that we see on these sources can be made in that way. And my final sort of thing I'd just like to share with you is some work I've been doing with students and postdocs at CAIPAC, and this is essentially what we do is look at very simple to highly stylized force-free magnetic field configurations. This is a periodic boundary conditions here. We just have a very simple, unstable magnetic field. In fact, it was thought that this was stable, but we demonstrated quite clearly it's unstable. It makes currents and charges. The particles get accelerated dramatically, and we can see the particle spectrum building up here. It's work led by my student, Yaji Yuan. And we see the energy that's released. And if we then go on to the next slide here, this is an all-sky depiction of what the gamma rays would look like seen from this source, looking all the way around it. And it's a very stylized source, nothing like the real thing in a jet. But what you will have seen there is a lot of fine structure. And I think on this slide here, you can see what an individual observer would see is a lot of these little spikes. So this is a highly stylized version of what will be going on, but it's very easy to imagine these jets becoming quite unstable and having these dramatic changes in structure, helicity preserving, if you like, changes in structure, which this is an example of, and yet what you see observationally from the relativistic particles are these highly spiky emission. So the extent to which that corresponds to the observations is very much work in progress, but we are quite excited by what we've learned so far from this model system. So let me conclude just with a summary which I'll put up here, and thank you very much indeed for the prize and also for the opportunity to speak to you, and I look forward to having discussions at the symposium on many of these topics. Thank you very much indeed.
Thank you very much for your quite stimulating talk. We have time for a few questions, please. Over there.
Oh, yeah. Hi.
Thank you very much for your talk. Very energetic. Near the end, you were talking about rather than the usual synchrotrons of Compton models or external Compton models of AGN, proton showers near the black hole. What are the consequences for neutrino observable emission for that?
Okay. I think, let me just back up a tiny bit and just say that there's been one of the many revolutions in high-energy astrophysics has been the detection of what I believe to be cosmogenic neutrinos at up to PeV energies from using IceCube. And there's now roughly 100 of these neutrinos that have been reported. And we know We don't know where they come from, but one of the prime candidates must be active galactic nuclei. And no one has demonstrated that. Now, I would personally say that most of the sources I've been thinking about have been electromagnetic. But if you take seriously the notion that protons can be accelerated to, say, 10 to the 18 electron volts or something like this in these enormous potential differences that are there for some particle acceleration scheme to take advantage of, if you say that you can accelerate protons to those energies, then some of them are going to stray out into the surrounding gas where there is an effectively thick target of baryons. And then when you get is not photopair production, but photopion production. And that photopion production is accompanied by neutrinos. And so that, I think, is the plausible way of getting neutrinos out of these sources. But the processes I've been mostly interested in and trying to calculate have been sort of electromagnetic processes within the body of the jet, which is very tenuous, and there's really not likely to be any serious plasma inside the jet. But if those high energy the protons, the hadrons, leak outside, then they can make the neutrinos.
Roger, good morning. I have a related question, because if you produce synchrotron radiation in the quasar, it should be also this electrons, relativistic electrons, should also be inverse Compton.
Yes.
Comptonize the broadline, right?
Yes.
Broadline region radiation, right?
Yes.
So do you see, or do you expect them somehow? Because these are very relativistic electrons, right?
Okay, yeah, absolutely, yes. No, let me just again back up a little bit to explain a little bit more what the problem is. I know this short. Okay, I'll use my hands as usual. Okay, so as I said, the simplest cartoon of one of these spectra is if we go from, let's say, radio at that end to gamma rays that end, is it's what I call it's two humps. So it's like a Bactrian camel, which is remember it's a bee like that. So it's unlike the other one. So it's like that. So what we've always taught our students is that's synchrotron, that's Compton. Now Compton is happening, that's absolutely clear. But what was observed in many of these sources was the Compton part was so high that required the emitting region, A, to be far out, and B, to be magnetically highly subdominant. And I'm doing this in the context of a model where the magnetic field is the dominant part because it's very close to the black hole. So if you're going to do that, then I think it's inescapable that it happens close to the black hole, its magnetic field, and responsible, therefore it has to be synchrotron radiation. Of course, there's Compton scattering going on as well, and in parts of the spectrum, that will be most of what you see, particularly when it's quiescent. So it's the biggest complication over the simple models that observers have loved and peddled is that it's a highly inhomogeneous source. You see emission all the way along the jet, and different parts in the spectrum are coming from different parts of the jet. And as I say, that's the sort of anatomical problem that we have to solve, and we haven't got there yet.
Roger, just one comment. We are learning quite a lot about formation of black holes from gamma ray burst. Very likely, we have sent a GCN a few hours ago that we are trying to see maybe the farthest GRB ever observed forming a black hole. We learn a lot from GRBs. In particular, a new concept, which is hypercritical accretion of up to a fraction of a solar mass per second on black holes. And the key factor there is the last stable orbit for the energetic, not the irreducible mass, not the ergosphere, but the last circular orbit, and the fact that you could have a lot of creation, and I go back now to the first question, of neutrino-antineutrino creating electron-positron pair. And the key for GRB and very likely active galactic nuclei are the electron-positron pair which self-accelerate, the one which we studied with Jim Wilson. Therefore, I would like to attract your attention on an alternative contribution just due to hypercritical accretion, neutrino antineutrino, E plus, E minus, and, of course, as usual, the dynamics, which is the dynamics of the electron-positron pair self-accelerating up to gamma 1000. And the baryon load with it.
Yeah. Completely agree, Remo. This is sort of a high end of the mass accretion rate that one has to contemplate around black holes. And in addition to the AGN, the gamma ray burst must be a prime candidate for association with these neutrino events. And we're in the hands of the observers to find not so much positional identifications, but temporal identifications. That's the way this is going to be sorted out. I promise to do that, Remo.
Okay. Thank you very much again.
Thank you.